Dr. Niayesh Afshordi, welcome to the podcast.
Thank you. It's glad to be here.
I thought we would have a more pedagogically oriented episode today, looking at cosmology as a field and me just getting to ask you all of the questions I've ever had. So, if that sounds good to you, the first question, it's a banger. What is cosmology? What are its subfields? What's it all about?
Uh, so it's one of those things that I remember when I first learned about cosmology, there was a standard textbook definition, a study of universe as a whole, history and a structure of the universe on its largest scales. But then when I became a cosmologist a few decades down the road, then what cosmology is became much more fuzzy. And uh, does it include a study of black holes or maybe epidemiology? I'm not sure. I ended up doing all sorts of things. And is that part of cosmology? Maybe to some extent. It does inform cosmology. But I mean, more traditionally, cosmology is a study of universe as a whole, trying to understand and model universe on its largest scales. Um, where we came from, where we go, and how things change across the universe on different scales and at different times. But then, as to subfields, it kind of ends up being different communities of people who study different things. So there are some community who look at, uh, try to observe the galaxies or other things that we see at late times. There is another community who try to observe and interpret what happens at early times. And then there is usually this distinction between observers and theorists. So people who kind of use pen and paper to do calculations and make models. And then there are others who use telescopes or other technologies to kind of measure things that inform us about the properties of the cosmos. And most cosmologists are actually somewhere in between. They do some theory and some observation. I never, well, I mean, I've used a telescope as an amateur astronomer, but I've never been to a telescope. I use data from telescopes, but most, even observational cosmologists who use data, they don't go to telescopes. There are people who get the data and then kind of send it over the internet or with disks, and then those are kind of used by cosmologists across the world to analyze and understand what they tell us about the universe.
So, how does astrophysics relate to cosmology? How do they are they the same thing, or is one a subdiscipline of the other? That's just a curiosity I have.
Now, that's an excellent question, and sometimes I introduce myself as a cosmologist, other time as an astrophysicist. So my degree is in astrophysical sciences, whatever that means, and I'm in cosmology and gravitation group here and at my university or institute. So it's kind of weird mixed things. In fact, yeah. So in one, I have two institutes. One of them in the cosmology group, and the other one I'm in the astrophysics group. So it's kind of, in some sense, you may say it's a distinction without a difference. In other sense, you may say it's kind of a historical distinction. So astrophysics kind of was derived from astronomy. Astronomy, of course, some may say is the mother of all sciences, where came from basically understanding the patterns and trying to predict the patterns in the sky. So what happens over time, basically in the past few centuries, was we learned about physics. So thanks to Newton and Galileo and everything that happened since, um, and started using physical laws to explain properties of or things that we see in the sky. So astrophysics is basically, in you may think of about it as kind of a way of doing astronomy by kind of interfacing it with physics, trying to explain things in terms of physical laws. Now it's really hard to separate astronomers from astrophysicists at this point. Um, Now, of course, I mean, cosmos, whatever we see about the cosmos is in the sky. I mean, there is very little of it that we can find on Earth. So you may argue that cosmology is a subfield of astrophysics. But depending on where in cosmology you sit, um, you may be closer to astronomy or maybe closer to physics. So, for example, if you're trying to understand the high energy processes in the early universe, formation of nuclei and subatomic particles is closer to particle physics. But if you're trying to understand the mergers of galaxies and what they tell us about the structure on larger scales, you're maybe closer to extragalactic astronomy or extragalactic astrophysics. So yeah, so that's these are all kind of related. Astronomy, astrophysics, and cosmology, they're all related with each other. But in some sense, for historical reasons, they are considered kind of different clouds of kind of interests.
Kind of reminds me of within philosophy, you have like the four main subdivisions of logic, metaphysics, epistemology, and ethics. And then and those are pretty cleanly distinguishable, but then you have a field like philosophy of religion, which doesn't map neatly onto that. That will involve elements of all four. So I wonder if there's a similar situation where you have the main divisions within physics, but then you have a field like cosmology or astrophysics or astronomy, which is by its nature going to be an overlap between different subfields. Is that perhaps right?
I mean, I'm not a philosopher, so
Oh
I
yeah, that part's right, I think. But with yours,
I don't want to say anything that offends philosophers, so I'm going to sidestep from that. Uh, but in physics, I mean, the clean separations. I mean, I think it doesn't exist really. So I mean, you could probably say who are the most distant physicists you could imagine, and probably there are kind of there could be two that have the least overlap. But to be honest, everything has some overlap with everything, and because people who work on them kind of use similar tools that are interested in similar problems. Um, and yeah, I mean, for my part, I mean, I've worked on various things that some usually people don't consider as part of cosmology, and others are kind of in the middle of cosmology. Uh, and yeah, I mean, I think is are kind of more like clouds that kind of fall off, but really it's kind of the definition is based on affinity of people in some sense. So if there are people who call themselves cosmology and there's some overlap in their interest, but there are also divergences in their interest. And yeah.
well, that's helpful because in some of these interviews, I'll look these individuals up and it'll list them as an astronomer or a cosmologist or an
Mhm.
astrophysicist or a fourth designation. But then it will cross-reference them in other ways, and I don't know if I'm offending anybody by ascribing a title to someone that say they don't actually have. But it seems like there's more fluidity.
I mean, certainly from my point of view, there is a lot of fluidity. Right? In
Hmm.
some sense, I mean, there is this question of inclusivity as well. That yeah,
Right.
people want to have some identity. On the one hand, so they want to distinguish themselves from others. On the other hand,
Right.
I
Like
mean, you
they're an
would think, I mean,
astronomer. I'm a cosmologist kind of thing.
yeah, right. So there is. I mean, do you want to be more inclusive, or do you want to be more exclusive? And then there is maybe some point to having like individual identities, I suppose. But at the end of the day, I feel more inclusive always better.
I agree. So within cosmology, what are your research interests? What are your favorite topics to study?
Yeah, that's one of those tough ones because that's something that's been expanding quite as maybe faster than the expansion rate of the universe. So it's uh, my interests have been very fluid. In my early days, I studied properties of so my PhD thesis, for example, studied a cosmic microwave background and what it can teach us about dark energy, which is one of the proposals for why our universe is expanding faster and faster, or what it can tell us about the missing baryons, which basically it refers to this puzzle. And most of the matter in the universe seems to be invisible, not just dark matter or dark energy, but also even the regular, ordinary matter in the universe. Uh, Most of it, not 90% of it, we don't know where they are. Um, so that's kind of where I started, but I kind of expanded my horizon, trying to understand better what happened at the Big Bang. And in term by that I mean coming up with more models or understanding models of the Big Bang. Um, And lastly, I kind of, in the past maybe 10, 15 years, I tried to get to the bottom of everything, which is theory of quantum gravity and what drives the universe, which is some intersection of gravity and quantum mechanics. And whatever we can learn about it, maybe from Big Bang, maybe from dark energy, or maybe from black holes and gravitational waves. So I've kind of tried to be equal opportunity. Any observation can tell us about quantum gravity, I take it, even if it's not traditionally considered cosmology.
So dark matter is an interesting one because I
Mhm.
don't know what it is. And I remember that I remember watching a documentary. I think I must have been 16 or 17, and
Mhm.
the scientist they interviewed gestured towards the chair underneath the desk over there, and he said, "There's dark matter. It's right there. It's
Mhm.
everywhere." What is dark matter? What's that?
Oh, that's excellent question. We have no idea. It could be many things. We know some things about dark matter, or certain things that some mysterious properties of the universe that we attribute to dark matter, but really we don't even know if it exists. So what we do know that exists is that the gravity in the universe doesn't appear to be driven entirely by visible matter. So there are things that we see. There's gas, there are galaxies, there are stars. So these are all the things that we can observe in the universe and study in exquisite details. But then we could also study the gravity, which, based on how fast things move and how fast they accelerate, you could measure the gravitational force. And it appears that most of the gravity that these celestial objects experience, at least on larger scales, is not due to visible matter. So we attribute this excess gravity to something called dark matter. And that's kind of um, that's the conservative answer, if you want. That's kind of the safe answer. But then we can go into the realm of speculation. If you want to be more speculative about what's responsible for this excess gravity, um, again, there are a range of answers. Again, it could be more conservative, which is maybe uh, there's a different type of particle. We know there are a bunch of particles. There are electrons, protons, neutrons in the universe. There are quarks, photons. Maybe there's another particle we haven't listed yet, and we call it dark matter particle. Maybe it's a heavy particle, heavier than proton. Maybe it's a light particle. Maybe it's neutrino or something like neutrino, which is like what the lightest particle we know. So that's been kind of a cottage industry for the past 2, 3 decades. Particle physicists cooked up different kinds of particles with different kinds of properties that could be responsible for this excess gravity. But if you want to be more speculative than that, maybe uh, it's a modification of gravity. So what we think is excess gravity, it may not be regular gravity of some additional matter. Maybe it's just the same old matter, but it gravitates in a different way. And there is another kind of line of thought that maybe that's what's happening. It's less popular because it's harder to make it match all the observations that we have, but it's certainly something that serious people have considered and are still studying.
All right. Well, that exhausts my knowledge of dark matter. But then I'll ask, was that scientist possibly correct when he said it's right there under the chair? I mean, I assume that if dark matter exists, it has to be ubiquitous throughout the universe at some level. It would be odd that it's only concentrated around certain galactic structures, but not here on Earth. But it would have to be such that we can't observationally detect it. So it's quite a mysterious thing.
Right. So, I mean, I think depending on its nature, it certainly could be that it's in this room at a very low density. And one of the very popular approaches to detecting, or attempts to detect, dark matter are these kind of large tanks of liquid gas or solid state matter, imagining the dark matter passing through this every now and then it hits the nucleus. And then we see evidence of that somewhere. So here in Canada, for example, in Sudbury, we have big underground laboratories looking for them. Unfortunately, none of them have been successful in detecting kind of convincing way the dark matter. But to be honest, that's not the only possibility. The thing is, we know on galactic scale dark matter has gravity, but that doesn't for that it doesn't need to fill the entire space. In fact, one model that when I was a graduate student I worked on was, what if dark matter is made out of black holes? Uh, this cannot be black holes that kind of we know exist in the universe, but rather some more exotic types of black hole that form at the Big Bang. They are known as primordial black holes. Um, so we don't know if that happened, but that's a theory, as good as the theory as any other theory for dark matter. And there are different kind of properties for these black holes that have been speculated. Some of them have been ruled out. Like, for example, in my PhD thesis, I ruled out some like very massive primordial black holes as a possibility. But there is a window of possibility for lower mass primordial black holes that could be dark matter. And then those are much, much rarer. They wouldn't necessarily be in this room or in the solar system, but they could be passing by every now and then. So there may be some effects, even gravitational effects in the solar system due to primordial black holes. So that's a different type of dark matter. That's not a particle per se, but it's still kind of lumpy like a particle, but just big particles.
I like the exotic gravity one, so I'm going to put my money on that one. That seems cool.
I think that's very popular with philosophers.
Yeah, well, there you go.
Unfortunately, it's not very popular with astronomers. And I mean, I can tell you the reason. It's just, it has been very hard to kind of fit the data with modified gravity. It's not that people haven't tried, but it's just much harder.
All right. Well, we'll see how it turns out. Yeah. So related to dark matter then, the other natural question is, what's dark energy? All this vaguely defined stuff.
So I just want to apologize on behalf of astronomers for naming things in confusing ways. I know it can be very easy to mix them up, especially if you are both dark something. But it's very different. So what happened, and dark energy is much newer, both in terms of terminology and in terms of its discovery. Dark matter was first discovered in the 30s by Fritz Zwicky, who was a Swiss astronomer. He was an odd character. He annoyed a lot of people, so nobody took him very seriously, even though he discovered a lot of things well ahead of his time. So it took a long time, another like 30 or 40 years, and much accumulation of evidence for people to kind of take dark matter seriously. But dark energy is much newer. So what happened was around the mid-90s, we started to have good models of the universe. So we discovered cosmic microwave background, and in fact even measured the fluctuations in the temperature of cosmic microwave background, which are the seeds, very, very like young and early seeds for a structure that later formed, and galaxies and planets were filmed, if you want, or we took snapshots of them where universe was much, much younger, a few 100,000 years old. So we had all these kind of interesting snapshots of universe at late times with galaxies, the structures in galaxies, and at very early times when it was just tiny ripples in primordial plasma. But they didn't quite match each other. So we tried to come up with a model where kind of these small structures grew and made big structures. They didn't work. Something was missing, it appeared. It wasn't quite clear what was missing. There was one kind of a straw that broke the camel's back. And that happened right at the end of 20th century, where we observed that the expansion of the universe appeared to be speeding up instead of slowing down. So by measuring the basic expansion or the speed of supernova that were exploding far away from us a few billion years ago, it appeared that they were expanding slower than they're expanding away these days, or universe expanding now. And that was weird because gravity is attractive, according to everything that we knew about gravity until then. But it seemed that things are speeding up. And there was one leading theory to explain that, was that there is some energy that fills the universe. But the thing that, of course, everything has energy. You and I have energy. But what is special about this dark energy is that as the universe expands, this energy doesn't decrease, doesn't dilute. And that makes it different from any other type of energy that we know in the universe. Like if universe expands, if there's matter, dark matter in it, it should kind of become less dilute. If there are baryons, if there are you and I, electrons, anything that's there are. I mean, you have a box and make it bigger, matter density in it goes down, but the dark energy density doesn't change. So, and that's what makes dark energy different from any other type of energy that we have, including dark matter. And it turns out that that's actually that can explain why universe the cosmic expansion is speeding up. But exactly what it is still a mystery. If it's exactly a constant, if it's exactly uniform, or actually fluctuates, these are all open questions. And even there is the possibility there that it's not even dark energy, but rather modified gravity. It's a different type of modification of gravity, but it's still possible because, again, it's not something we directly see. It's some property of gravity, or it's the acceleration of matter. And if gravity somehow works differently on very large scales, that could also explain this.
So this idea that the energy density of dark energy does not go down as the volume of the universe increases seems to entail that new energy comes into being. But how do you reconcile that with the conservation of matter and energy? Question from the layman.
That's an excellent question. And in fact, this goes to the heart of one of maybe most important property of dark energy, and that's the fact that it has negative pressure. So so if you imagine things are in a box and you kind of expand the box, um, so usually the energy in fact decreases, because there's pressure in the box, and then it kind of does some work on the boundary. So this is in fact a way of cooling down gas. If you have a gas in this box, and if you kind of expand it, it cools down, because the gas is kind of is pushing things away, pushing the walls away, and it loses energy. So in fact, you lose more energy than just you lose. That's the way of cooling down. That you don't just lose density by expansion, you also lose thermal energy through expansion for ordinary matter. But if there is something that has negative pressure, then the opposite happens. That if you kind of make the box bigger, there is negative work that's done. That means that instead of losing energy, this negative pressure gas in here would gain energy as the box expands. And it turns out basically if you have the right amount of pressure, this energy loss due to expansion would exactly cancel the energy gain due to the pressure force or pressure work. And in that sense, the dark energy doesn't lose its density, it just stays exactly constant.
Okay. I'll have to think about that one, but I think I understand it. So that satisfies my curiosity for the time being on dark matter and dark energy. And I want to talk about quantum gravity. But before we get to that, it would seem to make sense to say a word about what quantum gravity is the overlap between, and that would be quantum mechanics and general relativity. So I'm giving you an impossible task here, but as best you can, what are those two paradigms of contemporary physics, and why are they in conflict?
Yeah, that's one of those interesting questions. I don't know.
That's a tough one.
I'm possible. I'm thank you for giving me the opportunity to give it this give this a go. So the turn of 20th century, that was it overturned physics as we knew it. Before that, it was Newtonian and Galilean physics, which was all at its own kind of time was very revolutionary. Um, but what happened in 20th century, which was, I mean, in some sense, this is what general relativity and quantum mechanics had in common. Um, our universe becomes suddenly much more mathematical, if you want. I don't know if that makes sense. Um, in and the sense in which it became mathematical was uh, it became a theory of things that we don't see. Um, so when Newton came up with this theory of the solar system or Newton's law of motion, it was literally describing things that we could measure with a ruler or with a clock. Uh, but when we kind of started measuring things on very larger scales and very small scales, so that was basically the end of 19th century, beginning of 20th century, it became clear that things that we can observe are not necessarily things that we can directly plug into our laws of physics. Um, and basically, there were no laws of physics that could explain those observables. It turned out there were two sets of laws that people, the visionaries and founders of modern physics, came up with. There was, interestingly, Albert Einstein was on kind of both camps. So he came up with some set of laws for uh, microscopic scales, and then another set of laws for macroscopic scales. Um, but he's much more known for his set of laws for in the macroscopic and very large scales. So he realized that what we conceive as gravity is not a force, but rather a geometrical property of a space and time. So when we see something moves on a curved trajectory, when you throw a projectile or a satellite or a planet, it's not that it's being attracted by the sun, for example. It's trying to move on a straight line, but the space itself is curved, if that makes any sense. But it turns out that the math worked, and that is been one of the most successful theories. It's been withstood all the tests in the past century, and most recently we discovered gravitational waves that are ripples of the geometry. So this geometry is not that it is curved; it also this curvature propagates the same way that sound propagates in air, except that this geometry propagates in vacuum. There's nothing there that kind of unlike the sound that propagates in air. So that's kind of the story of larger scales. And the interesting thing is that this geometry we don't directly see. What we see is we can measure clocks, we have watches, and then we have rulers. Um, but the geometry itself, we don't observe it. There are some properties of it that we can observe, like distances. But the underlying kind of the underlying quantity that goes into the formulas is the geometry, which is not directly measurable. So that's the story on larger scales. There is an abstract form for it. It's called name for it. It's called metric, which is the term for this geometry. Now on the smaller scales, there was something similar. It has a different name. It's called wave function. And it turns out that that seems to be what goes into all our equations. So when we talk about what we thought or Newton thought were particles are actually waves in some kind of very complex, high-dimensional space. It's not like waves in the space that we see, but rather waves in some very abstract space. Still, it's called a wave function. And what we consider observables are some kind of derivative property of this wave function. So we don't directly measure the wave function in the same way that we don't directly measure the geometry or the metric. We don't directly measure the wave function. But everything that we know about quantum mechanics, properties of atoms and molecules and subatomic particles, can be described in terms of properties of this wave function and how it evolves. So these are kind of these two disparate descriptions. On larger scales, there is geometry. On a smaller scale, there is wave function. There is no unified language for both of them. You could kind of try to use the laws of geometries to describe quantum mechanics, or rules of quantum mechanics to describe geometry, but both of them kind of end up at some point with You try to calculate something, and then you end up with infinities of various forms. And this manifests itself in various places. For example, this is a simple one, very famous one. Hawking showed that black holes are not black. They have to evaporate because that's the property of quantum mechanics. They cannot be completely cold. The particles, due to quantum fluctuations, can actually escape the black holes. But then Einstein's theory of relativity predicts that nothing can go faster than the speed of light. So something that falls into the black hole cannot get out because it has to go faster than the speed of light. But if black holes evaporate, then things should eventually get out of black holes. When black holes get finished, if it completely goes away, what happened to the information within it? I mean, should have propagated faster than the speed of light, which Einstein said is not possible. So that's kind of one of the manifestation of this is inconsistencies, that you cannot write the same set of laws that describe both of these processes, quantum processes and geometric processes.
Okay, that's very helpful. The particular manifestation of this conflict might just be potential, because I know it's an area of controversy, but I was talking to Tim Maudlin about quantum entanglement, and he's a philosopher of physics who's contended that, among other things, entanglement needs to lead to a revision of relativity theory, because in a rough and ready way, Einstein's theory of special relativity says that nothing can travel faster than the speed of light, but on its face, quantum entanglement seems to indicate that what I do here can instantaneously affect something that happens at arbitrary distances away. And that would conflict with this idea that things cannot go faster than the speed of light. Do you think that quantum entanglement spells the defeat of the special theory of relativity, at least in some respect?
I mean, it's a long argument, but the short answer is yes. I think, yeah. I mean, it's a long and winding road, but at the end of it, I think, you come to the same conclusion. And in fact, I mean, I think that might be. I mean, there are differing points of view on this, obviously, but there is a camp that think that ultimately this property that nothing can go faster than the speed of light should be broken at the fundamental level. Exactly how it breaks, people debate about it, but it should be broken one way or another.
Interesting. Okay, well, now I've had two people tell me that, so I'm going to run with that forever. What are the main contenders for a quantum theory of gravity? Or I guess the preliminary question. We have these two paradigms. One can't be translated into the other. You get messy infinities, you get conflict. Why do we need a quantum theory of gravity? Why couldn't we just say, well, all right, we have these two inconsistent descriptions, but they work pretty well, so we're just going to let it go? What are the key phenomena that physicists are trying to explain that require the integration of both of them?
Very good. Yeah, it's interesting. Yeah, I mean, they are not things that immediately come to mind, at least when we deal with things on Earth. But I like to think that maybe, I mean, there are parallels in history that, I mean, most of the things throughout history, we had good working theories for everything. But then whenever we came up with better theories, then we could do much better things. And we kind of, our humanity advanced by solving paradoxes that seemed irrelevant early on. So, I mean, Newtonian gravity was developed to explain how things moved in the solar system. So it didn't have any immediate application, but of course now we use it every day, and even Einstein gravity has applications that are far-reaching. Now, there are places in the cosmos that we can see where it appears that these two theories, quantum mechanics and gravity, come to head. The most famous ones are Big Bang and black holes. So I already described for you what happens at the black hole. So black hole, according to Stephen Hawking, they should evaporate, but exactly what happens to their information, it's a question that we don't really know. Now you may think that, okay, it takes a long time for black holes to evaporate. Maybe we don't have to worry about it anyway. But it's not clear that's the case. And in fact, that's been one of the pivots in my career in the past century or so. Sorry, not the past century, the past decade. The gravitational waves were detected in 2017 or 2016 were detected, or 2015 they were detected, 2016 the data it was released. So it's almost a decade ago. And these are not black holes that are evaporating, but there's something amazing about them because gravitational waves give us a deepest view of what may be happening near the horizons of black holes. And it turns out that uh, almost all the solutions to this information paradox, that what happens to information when black holes evaporate, involve changing something near the horizon of the black hole. So we know that something must be going on there, some quantum effect of some sort. And now we have a microscope, is gravitational waves. So gravitational waves, people don't usually think of them as microscope because the gravitational wave detectors are kilometers long. But they are really microscopes we could use to actually study microscopics near the horizons of black holes. And if there is funny business happening there, we actually can see that. And I mean, there has been active effort trying to look for evidence of this funny business near the horizons of black holes. So that's one place where quantum gravity may be within reach. I'm kind of optimistic, but it will take some time. So there's been a lot of excitement and activity along that direction. The other direction, and should be surprising from your beginning, it's like Big Bang. Big Bang is the other place where you get to large temperatures, large energies at small scales, where quantum effects should become important in gravity. And in those cases, so we don't really have a good theory for the Big Bang. We have a lot of observations. So the observation is we see basically fluctuations of all the scales, these tiny ripples. They are very regular in some sense. And we've measured the amplitude of fluctuations, roughly 1 in 100,000. They are red. What that means is that if you look at long wavelength, there is a little bit bigger amplitude of fluctuation than there are on the small scales. So these are kind of very interesting clues that basically you have these two numbers. I wish there were more numbers we had measured. For some time, we thought we measured amplitude of gravitational waves from the Big Bang, but that turned out to be a false flag. So right now, we have these two numbers about what happened at the Big Bang. But the interesting about it is they don't seem to respect causality, or I mean, things must have propagated much faster than the speed of light to be able to generate these kind of fluctuations on such larger scales. Using relativity as we know it, you cannot really produce these things. So something happened at the Big Bang. Exactly what happened, we don't know. And well, we wrote a book about what have happened at the Big Bang. There are many possibilities.
Yes, well, a good segue, and then I'll direct it towards a question I had about quantum gravity. But go ahead and introduce the book that's coming out in May on many of these same questions, and what that book is going to look at.
Right. So uh, the story of the Big Bang, like much of the science stories, are kind of often told from a point of authority as established fact. That what happened at the Big Bang, what happens if you fall into a black hole, what happens if you go to the center of a galaxy, you name it. So there are all these kind of stories about established facts in science. Turns out that science is much, much more uncertain, and you may hear some popular accounts of what might have happened. For example, for the Big Bang, there is a story of how it went, and there is even a newer story is known as cosmic inflation, which is a period of accelerated expansion, kind of like what we know is happening now, but at much earlier times and at a much faster rate. And that is the predominant story of the Big Bang. But it's not as well known that it's still a story, and we don't have definitive proof or even very concrete evidence for it. It's just the most popular story. And there are many others that they could work in some sense better, some sense worse, and they could also connect to this deep puzzle of quantum gravity. That really the deepest ambiguity about the understanding of universe is not what happened at the Big Bang, but rather the fact that we have these two sets of inconsistent laws. So you can try to put a band-aid on it by coming up with a story, but really the problem is not the story. The problem are these inconsistent laws. And whatever, if you really want to solve the problem, you also have to come up with kind of the solution to this inconsistency. So we kind of went through other possibilities and how these other possibilities for the Big Bang may be related to this deeper problem of quantum gravity and basically paradoxes that we have in fundamental physics. So that's kind of the story of the Big Bang, and to be honest, there are similar stories with the black holes that you could tell. But I think the point of our book was to highlight two things. One is there could be one popular story, but that doesn't mean that's the only one. And the hallmark of science is that you have to have different stories and be able to test them. Just because there's a popular story, that doesn't mean it's the right one. And the other one is just the uncertainty and the uncertainty at the forefront of science. That the science, you have to kind of embrace uncertainty.
Mm. And the title of your forthcoming book is
Battle of the Big Bang. So we dig deep into all these conflicts, the conflict between various cosmologists who try to push their own pet theories of the Big Bang, the popular ones and maybe the fringe ones. And I had some of those, but I tried to be I try to be objective, and I have Phil who tries to kind of moderate my own enthusiasm for my theories, although that Phil, my co-author, I should say. But also there are other battles, the battles between the religious interpretations of the Big Bang and anti-religious interpretation of the Big Bang, the theist and atheist interpretations of the Big Bang, and the social kind of aspects of it. How much should we spend? What do we have to spend money, or is it a good idea to spend money to learn more about the Big Bang, or is it a waste of time and money? There are all these kind of various aspects and facets of understanding the Big Bang that have their own conflicts, and they're all happening at the same time. And so that's the story of that we're going to tell in exquisite details in our upcoming book.
excellent. There is a link in the description to pre-order that book, and I very much look forward to reading it. When it comes to, and I want to discuss the origin of the universe. We'd be remiss if we didn't talk about that. But just to continue on quantum gravity for a moment,
yes,
what are the leading today contenders for a quantum theory of gravity, and which one is your favorite?
Very good. So it's interesting that, again, similar to the question of Big Bang, if you ask people or even prominent scientists, they would tell you one story. And it's important to know that it's just a story and maybe the most popular one, but it's one of many. So the most popular one is not necessarily by most popular, but the most popular by the number of people who work on it is known as string theory. And that's the idea that the fundamental constituents of the universe are not particles, but rather strings, kind of tiny loopy things. They're either open-ended loops or, they're either closed strings or open strings. So it's exactly as they sound. And everything is made out of those. But it turns out that if you want to do this and follow the rules of quantum mechanics consistently, there are a lot of non-trivial implications. For example, one is that there needs to be 6 extra dimensions in the universe. They are somehow hidden, we don't see them. But somehow for the math to work out, You cannot do it in 3 space dimension. You need 6 extra space dimension for that to work. Um, and then there are other things. There are all sorts of strange things that exist in this string universe. There could be many different universes, sort of a multiverse. And what that means is that basically, um, uh, in some sense, the same way that you think there are different phases of water, there is like water, ice, and vapor, for example. So there are like 3 phases. Now, for a string theory, there are also many phases, but instead of 3, there are like 10 to the 500 phases. Um, and all of these should somehow exist somewhere in the universe. We cannot, because we cannot decide which one we are in. All of them should exist somehow. And then there are all sorts of other crazy explanations. Well, I shouldn't say crazy. There are possibilities. But I mean, to be fair, any possibility for quantum gravity is going to be outlandish because we don't really know what's happening. So all of these are very different from what we know. So that's one possibility. Another possibility is maybe geometry is really discrete. So what we conceive. So the same way that kind of the energy, when we thought about energy of atoms, classically we thought it was continuous, but really in quantum mechanics we realized it come in quanta of energy. Maybe geometry is the same. There are quanta of geometry. And that's the point of view in loop quantum gravity, something that many of my colleagues here at Perimeter Institute have been pushing for. Elias Smolin, my good friend here, whose office is just upstairs, and Abba Ashtekar and Carlo Rovelli. So they kind of started this movement. So that's another popular kind of direction, try to have a quantum theory of gravity. There are others. Another good friend of mine, Rafał Sorkin, proposed what's known as causal sets, where he kind of used the same approach of making things discrete, but instead of talking about discrete geometry, he thinks about discrete causality, if that makes any sense. So what Raphael and his friends kind of propose is that instead of a space-time being a continuum, there are discrete atoms, and the only relationship that these atoms have with each other is causal relations. So that's a different kind of discrete space-time. They're known as causal sets. But then my favorite, it's known as Hojava-Lifshitz gravity, which is in fact something I alluded to in our earlier discussion, that maybe things should go faster than the speed of light. In fact, Hojava proposed about 10 years ago that, actually now it's 16 years ago, yeah. He proposed that if you go to very high energies, then a speed of everything should go to infinity, a speed of propagation. So what you think is a speed limit, which is the speed of light, is not really a limit. It's only what we think is a limit at low energies. But if you reach to high energies, energy is comparable to Planck energy, which is the highest energy we think is there in quantum gravity, then things propagate infinitely fast. And that's a different way of thinking about different way of coming with a theory of quantum gravity, that this idea that Einstein had, that nothing goes faster than the speed of light, that was really the problem. So if you kind of let go of that, then these two theories, quantum mechanics and gravity, can actually live together happily. So these are kind of, I think, some of the ideas for quantum gravity. There are a couple of others. I don't know how many more you want me to go into, but yeah. So there are a few other possibilities as well, and they all have kind of their own loyal followings and proponents.
So it's very much an open question at this point. We really don't know what the correct quantum theory of gravity is. That's what I'm gathering.
Yeah, and I mean, the thing is, you may also argue none of these are really theories. So these are kind of ideas. So theory in physics, kind of having a theory is a very high bar. So when you have like theory of relativity or theory of quantum mechanics, So these are kind of very established frameworks where it have kind of gone through this scientific loop of kind of making predictions and being tested, and based on that, coming up with more detailed predictions. So all the things that we know as physical theories, or even theory of evolution, if you want, in biology. So these are high bars. And what we call theory of quantum gravity, I mean, we don't really have anything at that level. We just have kind of ideas or notions. But none of them have really made concrete predictions that we could test. Um, so yeah, so these are kind of ideas, and none of them have really kind of been. We all have our own bets, but none of them are really theories.
Well, I bet string theory is right. So that's
Okay.
that's where I'm putting my money. No real reason. I just think it's pretty.
Sounds good.
Yep.
I mean, I
So
think.
you bet.
Yeah, go ahead.
Oh no, I was just gonna say. So you mentioned the multiverse. I think
Oh.
a good segue into that topic is the cosmological constant problem.
Mhm.
What is the cosmological constant problem?
Very good. Um, so there's a strange topic in physics. It's called naturalness, and it's a bizarre thing. And I mean, we talk about it, and I mean, various stages in our career, and every time I suddenly think about it, it sounds bizarre in a different way. Um, I mean, if you're kind of an outsider, you think about what's natural and what's not natural. Okay, so you say things that happen in nature are natural, and things that don't happen in nature, I suppose, are not natural. But of course, I mean, if you're trying to come up with the right theories, we don't really know what's happening in nature, and that's the whole point. If we knew what's happening in nature, then it wasn't really an area of inquiry. So naturalness is a strange beast. Nonetheless, physicists have some definition of naturalness, and this definition has something to do with uh, coarse graining. So basically, um, I mean, imagine. I mean, I'm kind of you're looking at me. I'm looking at the screen, and I make my eyes blurry a little bit. Okay, so I could still kind of make out the kind of the broad lines of your face and what's behind you, but I may not be able to see the detail, and I kind of cannot make my eyes blurrier and blurrier, and this picture becomes a little bit fuzzier and fuzzier. But still, I mean, the broad structure looks the same. Okay. Now, it turns out that there are some things in physics that if you kind of make them a little bit blurry, the technical term for it is make coarse grained a little bit, um, they make very different. And those are, so physicists call them basically not natural. So that's not natural. Uh, and this kind of has to do with quantum effects partly because these quantum effects happen to be important on very small scales. But you would think that these are small scale quantum effects that are, I mean, very important. It shouldn't affect things on larger scales a lot, but if they do, then that's a problem. And the biggest kind of manifestation of this problem is the vacuum energy. So it turns out that the cosmological constant of dark energy is something that you could get from quantum fluctuations of fields like, say, photon or electron or other things that we know exist in the universe. Even if there is no particle, it's completely empty space. In quantum mechanics, there are fields that still fluctuate, just they're in vacuum, and those have energy. And this is a lot of energy. In fact, so much that when Pauli first calculated this, realized that the universe cannot fit the moon in it if you include the energy of these basic fluctuations of electron field. So it's a very weird thing, and there is a simple kind of cheap answer to it that somehow you add a constant that cancel all of these energies. So because this can be positive and negative depending on the type of particles that you have. Um, and somehow they exactly cancel each other. Maybe there are particles that we don't know and the ones that we know, and then there are other contributions to this vacuum energy. They all just cancel each other, and there's just a small value such that actually moon can fit in our universe and galaxies can fit in our universe. Um, Interestingly, there is this vacuum energy is not exactly zero. So the fact that we discovered dark energy, and now there is a lot of evidence for it, means that there is some vacuum energy. This at least dark energy is consistent with vacuum energy, but is 60 orders of magnitude smaller than those kind of energy that was predicted from quantum fields or quantum fluctuations of electron and say Higgs particle, for example. So that's the cosmological constant problem, that there are these contributions to the vacuum energy that must be there, but somehow they manage to cancel each other in a very unnatural way. So, and there is I mentioned this blaring your eye. Basically, the thing that, so imagine that you kind of make all of these energies cancel each other very precisely. But now if I blare my eye a little bit, so basically change the structure on a tiny scales a little bit, this cancellation goes away. So it's a very fine-tuned cancellation. So you have to cancel very large numbers against each other. And somehow if one of those numbers is a little bit different, then this cancellation is destroyed, and then somehow you have this big vacuum energy again. So it's a very strange problem, because it's not that something that happens necessarily dynamically, that is, so you have to kind of put it by hand somewhere and then it moves away. It's a statement about constants of nature. And so if there is a fine tuning of these constants, um, does it mean it's unnatural, or is it just mean we just happen to be living in this fine-tuned universe? And yeah, so I mean, different people have different feelings about it. It would be good if things are not fine-tuned, and in fact there are not a lot of these constants that are such fine-tuned. There are really two of them in physics as we know it. There's cosmological constant, mass of the Higgs boson. The rest of them are much more natural. um, so yeah, so that's the story of the cosmological constant problem.
When it comes to the cosmological constant, especially, it's important to keep fine tuning, the general concept of fine tuning, distinct from what's called anthropic fine tuning. Because it's my understanding that you can have a theory in physics that's fine tuned, but that doesn't necessarily mean that one is referring to what has come to be known as fine tuning for life. So, the cosmological constant problem, is that a problem just about a general coincidence, this unnatural phenomenon that these huge field values cancel each other out to this small value, and we want to know why? Isn't it also the case that any deviation from that observed value one way or another would render the universe life prohibiting? So not only is there this general kind of coincidental alignment, unnaturalness, that value is also fine tuned for the existence of life in the universe. And that's what makes it even more outstanding that it happened, and perhaps demanding some sort of explanation. So my question for you then is that a facet of this problem, that the constant appears not just to be fine-tuned in this general sort of sense, but fine-tuned for life?
Right, so um, this is a very good question, and I think that the problem is that there are kind of several ambiguity in this. That, I mean, of course, I did tell you what the problem is, at least what people tell you as the problem, but there are all these kind of ambiguous elements. Um, so I tell you a story about these numbers canceling each other, but that's a story in the context of a model. Um, but we know it's an incomplete model, right? Because we already been discussing that we don't have a quantum theory of gravity, right? So I have an incomplete model, and I'm saying that, okay, so in this incomplete model, there are these unknown numbers, and somehow these unknown numbers and in this incomplete model should cancel each other. But maybe in the more complete model, it's not uh, it's not the fine tuning. So maybe these are not really unknown numbers. They're also sort of the more complete model. What completes the model also makes these cancel each other. So that's certainly one possibility. So this kind of presumption of fine tuning, it's it's kind of, we are guessing what the full model is, but then we don't know what the full model is. Um, the other part of it is kind of, the whole thing is weird, that um, I mean, it's not that someone is deciding what these numbers should be. Like, what is the physics? When we talk about fine tuning, what is the process? I mean, we certainly are not thinking that some kind of old guy with a beard that sits there and, okay, so, okay, should I put this number to this one or this one, or are they going to kind of fine tune it by hand? So that's, I mean, that's not the picture that physicists certainly have. So so what is this that we mean by fine tuning? It's a strange thing, I'd say. Now, so I think I didn't kind of quite finish talking about the multiverse. So one possibility of thinking about this is that, okay, so maybe in this huge vast universe, various places, various possibilities for all these numbers exist, and in some place it just may happen to be that the numbers happen to cancel each other. I mean, if you have this line that you kind of draw some random jagged line, sometimes it may cross zero, and so that's, maybe we happen to live there. So that's one way of kind of not having to worry about what fine tuning means. Maybe, I mean, there is no tuning. There are these numbers that exist everywhere across the universe, and that's the idea of the multiverse, that we live in this vast cosmos where various places, various kind of constants, well, these couplings or numbers or cosmological constant or other things may take different values. And then I mean, yes, so we happen to live where we can. So indeed, this question of fine tuning for life, it's something that's by necessity. I mean, if we measure something, then we should exist there to be able to measure it. So so that's so whenever we measure something, then it must be fine tuned for life, because if it wasn't, we wouldn't be able to live there to measure it. Um, but yeah, indeed, that fine tuning is different from fine tuning that's I mean, this idea of naturalness. So the idea of naturalness has to do with that, if you kind of, as I was saying, you change the small scale things, you kind of blur your eyes in kind of intuitive sense. Does the larger scale physics care a lot or not? And that's the fine tuning. That, so if it cares a lot, then there must be some fine tuning involved. If it doesn't care, then there is no fine tuning. So that's the fine tuning that physicists talk about, and fine tuning for life is okay. So that, then the other aspect of it is, okay, what is life? And that's an entirely different Pandora's box, basically, because of course we are familiar with the life that we live, um, but yeah, so maybe you kind of define life as something very specific, someone with I don't know, with the curly hair, with I'm not sure, I'm trying to describe you. uh, yes, with some light beard, and maybe 1 or 2 days. You have some facial hair, some mustache. So that's, if that's your definition of life, that might be very, very special, and you can probably come up with whoever their first name starts with M, the last name starts with D, and so you can kind of be very specific about what you call life, and then that seems to be very rare. Um, but then if you only know yourself and you don't know anyone else, then that's the only life you know. But there could be many different types of life, and that's the other thing, is that yes, we only know the life that we know, and in some sense, yeah, if you kind of are always focused on one thing, then it might be look very special and rare. But if we know about other types of life, maybe, yeah, they could exist in a very different universe. And yeah, since we cannot really define life in a satisfactory way, so that's the other thing that seems ambiguous to me.
So, my area of research as a philosopher concerns the fine tuning argument for theism, the attempt to connect fine tuning for life to a design hypothesis, some version of the old man adjusting the dials, but in a more charitable sense, I suppose. And I want to get your take on what's the usual counter response to that reply, this kind of ambiguity concerning how we define life. The usual retort is that we don't really need to define life in any precise kind of way, because the consequences of changing the values for some of these fine-tuned features are so disastrous that no kind of life could exist in the circumstances. So, for instance, I have in mind the claimed fine-tuning of the neutron mass, the relative neutron mass relative to the proton. So the idea would be if you increased the mass of the neutron by 1%, then neutrons would have essentially immediately decayed into protons, and you would have nothing but hydrogen in the universe. And then if you decrease the mass of the neutron, all protons would have decayed into neutrons. Once again, you would just have this soup of neutrons. And in either case, you wouldn't get any life whatsoever. So that we just don't really need a precise definition of life to understand that there is a fine tuning for life of any kind going on here. What do you think of that reply?
Yeah, I mean, um, it's really a high bar for me to be. I mean, I know. I mean, um, molecules are complex. So if you say there's only, the hydrogen is the only thing that exists, um, well, okay. So I have to kind of try to sit down and imagine how what complex things can exist in the universe that doesn't have neutrons. But I mean, there are kind of different ways to think about it. One is that uh, so yes, neutron is some particle, but it's not the fundamental it's not the fundamental constant of nature. It's indeed true that if you change fundamental constants of nature, then then things could be different. But but exactly which constant am I changing, and why am I changing this constant and not constant, not that constant? So there could be um, yeah. So that I think this question of how stable the life is, it's, I mean, I can certainly agree with you that the life as we know it could be very different. I mean, may not exist if I change the constants. Um, but there's no complex structure exists. That seems like a much higher bar. And given that we cannot really, I mean, we don't really know where life comes from, right? So so I feel, on one hand, I feel like I'm underqualified to answer that question. That kind of how much complexity is necessary for life to come about. Um, but I feel the type of complexity that may lead to life may come about in different ways with different constants of nature, and yeah. So but even if fine tuning is there, and somehow we live in this island that if it's very elsewhere in the parameter space of possibilities, no one can live. Okay, I don't know what to do with it. So yeah, so maybe universe is fine tuned for life. Maybe if we change the parameters, the universe would be very inhospitable. But so what?
Mm. So there are then two questions here. The first is the universe fine-tuned for life? And then you have to deal with this issue of defining life and determining the consequences for varying the constants. And then there's the second question of, all right, let's suppose there is fine-tuning. Well, then how do we best explain it? And the multiverse is, I think, you correct me if I'm wrong, the leading scientific attempt to explain fine-tuning. And I like what one physicist gave as an analogy. He said, imagine going into a shoe shop and they only have one pair of shoes and it happens to fit you exactly and precisely, and also to be your favorite kind of shoe. Well, that would be a huge coincidence that demands explanation. It wouldn't be reasonable to say it just happened by chance, that they randomly only have the one shoe that fits you and that you like. And that would be the analogy of if there is only one universe, it just happens to have all these features fine tuned for life. That would be unreasonable. But then the multiverse, the analogy of that would be going into a shoe shop and they have every kind of shoe in it, of all sorts of styles and looks and every size. Well, then it's not coincidental at all that they happen to have a shoe that fits you. And so similarly, if there's a huge ensemble of universes with all different randomly assorted features, it's no surprise that one of them is fine-tuned for life. And obviously, we could only evolve and exist in just that universe. So what's your take on the multiverse as an explanation for fine tuning? Because I know that the multiverse itself is an area of controversy among scientists and cosmologists. Some people think of it as just kind of a God substitute, it's this unfalsifiable metaphysics. What's your take?
No, I think this is an excellent question, and indeed, it's this area of controversy. Um, I'm I'm kind of thinking about your analogy of, okay, if you happen to go to a shoe shop and then you see that there's just one pair of shoes that exactly fits you. um, there is obviously a backstory to that, right? Because you you're imagining there, you so the reason it seems atypical to you that other people exist and have different shoe sizes, and you know of other shoe sizes. You've kind of seen this story before, like walking into shoe sizes, and then most cases shoes don't fit you, right? So there is a backstory, and then you say, okay, so compared to that backstory to this thing that you've experienced throughout your life, this thing doesn't seem to fit. So this seems weird. The problem with the universe is that we only have one of it. We don't really have the backstory. We're trying to make up the story, and we don't really know. We don't have anything to compare it to. That's why I feel it's different, that we cannot. I mean, we could certainly try to come up. I mean, with similar backstory as a shoe shop with lots of shoes, uh, because we are familiar with that story. But uh, this idea of fine tuning, it in some sense kind of it involves a notion of probability that requires a lot of experience. Basically, it requires that you've tried something many times and you've seen that it works in a certain way, and then you say this is different. Okay, but if we just have just one example of the universe, it's impossible to define these probabilities, right? Because there's just one example. Now, I mean, that's certainly one point of view, that it's hard to kind of assign a probability to this. I mean, I think that I feel this is a valid caveat. The other issue with multiverse is, as exactly what you said, is that you kind of you construct this whole song and dance about entire universes out there, but then if you cannot really see any of that, is that science? So if you cannot test it, if there's really no testable prediction, is there really any distinction between that and a fine-tuned universe? I mean, may have a more satisfying story, but there is no way of distinguishing that from uh, from a fine-tuned universe. So, in some sense, by Occam's razor, you may think that the simpler, albeit fine-tuned story might be better one. But yeah, I mean, from the scientific standpoint, you cannot really distinguish these two. Um, and of course, I come back to this thing that I said before, and I don't think it's appreciated, that all of these fine tuning arguments are based on this assumption that we think we understand the full theory, which we don't. And it could be that the fine tuning goes away when we understand the full theory. And yeah, and I mean, I think finding the full theory may be a higher priority than solving the fine tuning.
I think you're right. And I've pressed advocates of the fine tuning argument with that point before. And it's one that bothers me, that our physics is not complete. We're
Mhm.
making extrapolations and
Yeah.
conjectures about the final theory and saying that, well, our incomplete theories are fine tuned. And so probably the final theory will be as well. But we don't know
Mhm.
that. We don't know
Yep.
that. I don't see any principled way to ground the
Mhm.
claim that our current theories reflect the final theory in those key respects. That is to say,
Mhm.
with respect to fine tuning. So it gives me pause. But
Mhm.
I also think it's kind of a compliment to the reality of fine tuning that many cosmologists are exploring the multiverse as an explanation for it. I mean, they seem to
Mhm.
think this is a real problem that will endure, despite the fact that our physics isn't complete. So that at the same time makes me go, well, maybe there's more durability to the phenomenon of fine tuning in that case?
I mean, of course, I always think, okay, so there are, I don't know, 3 billion people who are Christians in the world, and 1 billion Muslims. Just the number of
Mm,
people following certain tradition doesn't necessarily
sure,
mean it makes it more correct. um,
sure,
yeah.
sure.
So there. Yeah. Anyway, so there you have.
Fair enough. Absolutely fair enough. So the other aspect of cosmology, which my newfound phrase is, we would be remiss if we didn't talk about, is the beginning of the universe. The probably main cited argument from apologists, religious apologists, and theistic philosophers more broadly is often the Kalam cosmological argument, which is a simple syllogism that one, everything that begins to exist has a cause, two, the universe began to exist, three, therefore the universe has a cause. So that second premise, that the universe began to exist, I think I know your answer. But do you think contemporary scientific evidence indicates that it's true? That space time had a beginning at some point in the past? And if not, why not?
What is true is our description of a space and time become more ambiguous as we go to earlier times. Uh, what happens at that point is a mystery. Whether the universe could have started at that point, or a space or time could have started at that point, or may have existed before that, but using different laws. Um, those are both possibilities, basically. So yeah, so there's certainly a class of cosmological models where they start at one point. Um, um, of So the time doesn't kind of go on forever, but there's a separate class where the time goes on forever, just but using different. You have to use a different set of laws to kind of to bridge between like the late universe, the universe after the Big Bang or before the Big Bang, if you want. Uh, or it could also be that everything goes in a cycle. So you need new laws at some point, and we know we need new laws because quantum mechanics and gravity don't work together very well anyway. But yeah, so something goes wrong. Exactly what goes wrong, we don't know. But yeah, whether there was a start or not, we have really no certainty on that.
What about the often cited counter reply of the Bordet-Guth-Vilenkin theorem, which ostensibly is independent of any quantum theory of gravity? This is the theorem that any space-time or universe which is on average in a state of cosmic expansion throughout its history cannot be eternal in the past. There's a more technical way to state it, but that seems to be right. And that theorem holds even under models of the universe which don't obey Einstein's theory of gravitation. And so it would seem that as long as that one condition is met of average cosmic expansion, we would have to conclude that the universe had a beginning. Is that not a good argument for a beginning of the universe?
I mean, I mean, there is this one simple caveat that why should there be universe expanding? Maybe it was collapsing and then bounces. I mean, that's one obvious caveat. The other thing is, if you actually look at the proof, there's a something technical that you prove. That basically, what you're proving is basically if you have a line, basically which is a trajectory of a particle or photon, it ends at some point. Uh, but we know real particles are not don't move on lines; they're quantum. So we have quantum fields. We don't have lines of particles or point particles. So so that theorem doesn't say anything about quantum fields. And yeah, so that's and I mean, so it is really a theorem about this classical space time, uh, but we know quantum mechanics tell us space time should be quantum at some level. Classical space time doesn't work. So there are all these caveats to that Border-Guth-Vilenkin, which I mean they know about it obviously as well. And I mean there are many many models that universe doesn't start, and of course there are some that they do, but there are many others that don't start, uh, and that's perfectly fine. Some of them have a collapsing universe that bounces, and other ones you do something else with the space time that makes it different and doesn't exactly satisfy the assumption that is that theorem.
To zoom out, I've recently heard it said, I can't remember who told me this, but it stuck with me. They said that cosmologists are really only interested in the origin of our observable universe, the origin of our patch of space-time that we can observe. They're not really interested in these deeper, perhaps more metaphysical questions about the origin of space-time itself. And the context of that conversation was when I talked about some of the theorems within philosophy of physics that seem to indicate we can never know about the global properties of space-time as a whole. And they said, well, cosmologists aren't really interested in that anyway. My impression is that cosmologists do care about the origin of the universe, big U, space-time as a whole, not just our observable patch. But I wanted to hear from you if that was a correct impression on
So
my part of there.
it's good to circle back to how we started at who is a cosmologist.
Right,
And
right.
I think your friend was probably talking to a certain class of cosmologists. And
Sure. Okay.
yes, so there are different kinds of cosmologists. Uh, it, I mean, from my own experience, in fact, I had a paper a couple of was it 2 3 years ago with Jao Maguejo, who is another cosmologist in Imperial College. He's also a proponent of this faster than the speed of light cosmologies. And this was exactly about a universe, things that are much bigger than our observable horizon. Uh, but we had an argument that used that size, a size that was much bigger than an observable universe, to explain why cosmological constant is so small, basically to solve the cosmological constant problem. But that actually involved studying a patch, what we call the classical patch, which was much bigger, I think 10 orders of magnitude bigger than our observable universe. But that's what basically was necessary to actually explain the small value of the cosmological constant. So yeah, I mean, we are not you cannot confine cosmologists within a box. Is that we are very fluid bunch. We go wherever our theories take us, and I mean, I think, to be honest, I think a good cosmologist should try to make predictions, and that's the goal. Either try to test the predictions of a theory, but ultimately that's the thing, that observable uh, we want observable predictions, but that doesn't mean that our theories are bounded by observable universe. The ingredients of the theory could be everywhere, but ultimately you want to lead to things that are observable, or at least some of the features or facets of your theory should be testable, and that's, I mean, basically the aim of the scientific method. I should say this story of the multiverse is also interesting because of the notion of this many word interpretation of quantum mechanics. And that's another reason that cosmologists and kind of, uh, I guess, maybe quantum people who think about quantum cosmology um, take multiverse a bit more seriously, because there is this idea of what happens when you make a measurement in quantum mechanics, and the idea is that maybe somehow all the branches of the wave function live across the universe somehow, and then when you make a measurements, you actually find, kind of constrain your locale to places where certain certain things are true. So this is yeah, so there are some cosmologists, I mean, I consider myself part of them, that we also think about these philosophical aspects of quantum mechanics and wonder whether they have a cosmological interpretation, for example, the measurement problem. Yeah.
I think it's fitting to round out the conversation on a more philosophical note. And even though the fine tuning argument is my area of research, I don't really have a dog in the fight. I'm genuinely just interested in it intellectually, and I want to find out the truth about it. Is it a good argument? Is it sound? And I don't have a view on that final assessment. But I want to hear from you as a cosmologist coming from the other side, because I'm a philosopher looking into the science, and you're a cosmologist who's touching upon topics that have philosophical significance as well. What is your opinion on attempts like the Kalam cosmological argument or the fine tuning argument to connect modern scientific discoveries to theistic conclusions, to conclusions about God's existence? This is a very tough question. Obviously, it's about how does science relate to religion? But obviously, when you're talking about the ultimate explanation for the universe's features and the origin of the universe, typically those have been domains of religious and philosophical reflection. So it's inevitable that we're going to ask, is there room for God in modern scientific understanding? So there you go. That's a big one. But what on all of those things I asked you, anything you have to say would be interesting.
Wonderful. Yeah, I'm come with. I have a secret weapon. We actually have a chapter of our book, which is, uh, it's called "Religion of Science and the Science of Religion," or I cannot remember the order, but um, and we kind of, Phil and we come from different backgrounds, have somewhat different views in this. Um, but kind of my point of view on this is, philosophy, religion, and science. Ultimately, these are what we use to interact with our environment and with each other and our world. So these are kind of approaches that humans have to to life, right? So, and in some sense, they all have played significant roles throughout history, right? It's impossible to deny the role of philosophy, religion, and science in how history has developed. And it's also impossible to imagine that they would uh, disappear as a driver of humanity or human condition in the future. What I'm kind of what I'd like to highlight is, as much as scientists would like to think that they are rigorous and then they they kind of follow scientific method, it's somehow illogical to imagine that whatever that led religious kind of tendencies as humans for millennia is just as it disappeared in scientists. So um, there must be whatever that drove religiosity of our ancestors or many of our peers these days. It's not that it's not there in cosmologists. I mean, they have the same ideas. They kind of work in similar ways. They may not call it Christianity or Islam or whatever. Um, but how do we know that basically our models of the Big Bang right now, and there are many of them, or our models of quantum gravity are better than creationist stories of Bible or Quran? And I mean, there is this some things that we know. We think there are should be testable theories, so there are observational tests. But many things, like things we discussed today, like multiverse or um, others, cannot be tested directly or even indirectly. There's still people have strong opinions of them. String theory, loop quantum gravity, inflation, bouncing models. Some of them cannot be tested, at least in any way that we know right now. Some of them are hard to test, or tests are controversial. Um, are they really better than kind of old mythologies that we have? And I feel that these are all parts of our conditions. I mean, philosophy, religion, and science. And I don't know if it's the kind of answer that you're looking for, uh, but I feel that I mean, yeah. So there is a religion in any cosmologies, and they may not want to admit it, but there is a religiosity into their approach, which does drive them, and I think we should kind of make our peace with it, that it's part of us, and whether God is part of this story. I mean, it's something that I struggle with, and I feel that there is a role, because science tells us about the facts of life, or how we can learn about the facts and how the nature works. But it doesn't tell us how to interact with each other and uh, with our environment. It kind of tells you what actions lead to what consequences, but it doesn't tell you how to pick what consequences you desire. And God is, our creations or religions are things that kind of we have to answer that question. And it's hard for me to imagine that we can live in a world that we don't have these kind of guidelines, and we may call it God, we may call it something else, but these things will exist and they will be outside the realm of science proper. Um, but they will interact with science as they have throughout history. So yeah. So I mean, I feel that these will exist, and hopefully we'll learn to coexist together better as we learn learn well, as we learn to do it better, but maybe not.
Well, Niyesh, this has been a fascinating conversation. I think it will prove helpful to people. And thank you for coming on the podcast. I remind people that your book is Battle of the Big Bang. It's out around mid-May, which is also my birthday. So that's cool. And I appreciate you taking the time to come on the podcast. Thank you.
It was a pleasure. Thanks, Miles. And hopefully maybe we just can meet in person at some point.
I agree.